So today we are going to discuss about graphs, and to a normal person, a graph is something of this sort with a x and a y axis, and in these axis or coordinate system, you have some curve which express something, and you are able to find the area under the curve, and there's a smooth line or it might be a jagged line, or there you might have seen something of the sort of a bar graph or a histogram. So to a normal person or other statisticians, graphs means something like this, but to a mathematician, graphs have a very specific meaning and a concept, and it looks something like this, which we're going to study formally in a little while. So for a computer scientist, a graph, and specifically a directed graph, consists of a set of vertices labeled V and a set of directed edges, and we call this set E. And moreover, the set of directed edges is a cross product of the set of vertices, or I should have said it's a subset of the cross product of, or the Cartesian product of the set V. So as you might recall, whenever we have a Cartesian product on a set V or any set, so the result that you get is in a form of a ordered pair A B, such that A and B are members of the set that we are concerned with, and in this case it's V. So therefore, when we say that a set of directed edges and we label it V, then E consists of ordered pairs of the form V and W, where V and W both belong to the set of vertices. And what this implies is that there's an edge going from the vertex V to vertex W. So to summarize, we have a set V of vertices, and it might contain something like V, W, X, Y, or it might contain simple letters A, B, C, or D, or it might even have something of the form V vertices V1, V2, V3, and V4. And when we are using them in practical, for example, for a bus route or a network, for a computer network, these vertices might represent cities, they might represent bus stops, they might represent computer nodes, they might represent IP addresses, and you because graphs have so much applications in many diverse fields, it can represent anything. Or if it's a graph of your uh, network of friends, it can be even persons, and the edge between each node represent whether the person is a friend or not. And if you're talking about a bus route, then the edge will represent whether the bus travels from this bus stop to the other bus stop or not. So in a directed graph, an edge in set E does not implies that we have a way back from that edge too. So you must be careful of this, that when we say that there is an edge VW in set E, it does not means that we necessarily have an edge WV member of it, because it's an ordered pair. Had it been not been an ordered pair, the reverse would have been true. But since it's an ordered pair and it's a directed graph, it does not mean that having a edge from V to W does not implies. Sorry, I should have used the symbol implies. It does not implies that W has an edge to V. I should have used implies. Okay. It does not implies. So I'm using double equal to an arrow to distinguish from this notation of an edge. So that's what this node is saying. This node is saying that if you have an edge v going from vertex v to w, it does not necessitate that you must also have an edge going from w to v. It's an ordered pair, it's a directed graph, and that's not always the case. If that is the case, you will have a separate edge going from w to v. So here's an example. We have three vertices, A, B, and C, and that can be practically anything. They can be cities, they can be persons, or they can be computer nodes or IP addresses, and anything. And then we have set E, which specifies which nodes are connected to each other. So we can clearly see from the diagram that A is connected to B through this yellow arrow, and we have an ordered pair going from A to B. Then we have an arrow going from A to C. That's why we have a ordered pair A to C included in our set of edges. And then we have an arrow going from C to B, and that's why we have an uh, arrow going from C to B. So vertices are the circle dots, and they are called vertices or nodes. And edges is the arrow or the connector between two vertices or edge or nodes. So this right here is an edge, and this right here is a vertex, and the plural is vertices. And what's so interesting about directed graph is that directed graphs are directly related to a binary relation. So we have seen binary relation earlier in our topics in discrete mathematics, and each binary relation can be represented using a digraph or a directed graph. So and every edge in a digraph is a binary relation from each of the vertex or the set in a binary relation, and each element in those sets and domain and codomains are a node in a digraph. So that's a nice thing to know. So now we have a success of a few new concepts regarding graph theory, and we will tackle them one by one. So the first concept that we have is that of a walk. A walk is nothing more than just a travel of successive edges or crossing of successive edges. So if there's a person, let's assume that these are name of some famous visiting spots in the city, in any city, and there's a person standing at vertex A. So if he goes from A to C and C to E, then E to D, then D to B, then back from B to C, and then C to E. So this is a walk. It's just a a walk just follows successive edges. So it might will not be a walk if you skip an edge. For example, you say that okay, somebody went from A to C, and then he directly went from C to D, or from E to D. So this is not a walk. Why? Because it's not successive edges. These edges are apart, and then and and the assumption is that you are not a Hulk or a Superman that you can jump a walk or jump a edge. You have to walk through that edge. So it's considering that you are a normal human being, and the only way that you can travel is by walking. So you don't have any glider or any jetpack that you can escape uh, escape an edge and directly go from E to D. So if I remove an edge here, so this will not be a walk. So if I have a representation like this, that a person went from A to C and then from C to D. So since there is no edge from that goes from C to D and then from D to B, for example. So this is not a valid walk, not a walk. And even if I say that somebody went from A to C and C to E, and then he went from D to A, this is also not a walk because there is no edge going from A to from D to A. If there were an edge going from D to A, this would have been valid. But since we don't have any such edge in the graph, so that's not a valid walk, because a walk is a travel along the edges in a provided in a graph. So the next concept that we have is that of a length length of a walk. And length of a walk is nothing more than just the number of edges in the walk. So in our example, the one in the slide, we have 6 edges. We have an edge from A to C, C to E, E to D, D to B, B to C, and C to E. So these comes to 1, 2, 3, 4, 5, 6. So we the length of the walk is 6, because in this walk there are 6 edges involved, and it's not 7. It's not the number of vertices that you cross, it's just the number of edges that you have been through. Now we have the definition of a path. A path can is a walk that cannot repeat vertices. So you can say that every path uh, is uh, is a walk, but not all walks are path. So a path cannot repeat a vertex. It can repeat an edge though, but it cannot repeat a vertex. I'm sorry here. You cannot repeat an edge either, because if you repeat an edge, you will definitely have to repeat a vertex. So neither you cannot repeat a vertex even. So how can you repeat an edge? So so the point here is that every path is a walk, but not all walks are path. And the one thing that the path does not allow is that you cannot repeat a vertex. So a valid path would be going from A to C, C to E, E to D, and then D to B. And now you are kind of stuck here, because if you take this edge that's from B to C, if you try to take this edge, you would repeat a vertex, and which is not allowed in a path. So if you do this, it will become a walk and not a path. So you cannot take this edge. So and there's no other edge that you can take. So you are kind of stuck here, and the path is just going from A to C, C to E, E to D, and D to B. And the other thing is that again the length of the path is 4, and it's the number of edges that you cross, and it's not the number of vertices that you cross. So each path or a walk can be represented in a computer program using 2D arrays, or you can just say a table, or you can see a multi-dimensional 2D array. And what you have is that each row and each column represents the vertices, the set of vertices. And for every edge that connects two vertices, what you do is, if you're considering the edge E here, and we are considering the vertex E here, so we will go to the column E, we go to the row E, and if you're concerned with this edge here, this edge is connecting E to D. So we go to the row E all the way to the column which says D, and we will just write a 1 here. And that's we call, and we'll continue doing so for all the edges and all the vertices. So here's another edge that goes from E to A. So we'll go to the column E, or to the row E, all the way till we reach the column A. And once we do so, we write a 1 here. So one more example before we move on. So if we are considering the node C right here, so C has only one edge going out from itself, and that's to E. So we will go to the row C all the way to the column, to the row E, and we just write a 1 here. So if you continue doing so, you will end up with this table, and all the squares that don't have anything written in it are basically zeros. These are all zeros. And what it says that there is no edge going from B to A. There is no edge between B and D. There is no edge from going from B to D, and there is no edge going from B to E. Similarly, there is no edge going from C to A, or C to B, or C to C, or C to D. There's only one edge going from C to E. And so you just put zeros where there are no edges, and where there are edges, you put a 1 there. So this can perfectly very well be represented using a 2D array in a computer program. So we'll come back to this proof later on. For now, I need to mention this, that we have very alternating definitions and terminologies for walk and a path. So in some terminologies, walk might be called a path. So some papers or some textbooks might refer to a walk as a path. And a circuit or a cycle is a path that starts and ends at the same vertex. And a simple circuit does not have a repeating edge. And a simple path does not repeats any vertex. So a simple path is equivalent to a path in our terminologies. So what we have considered as a path, some books or some terminology or some papers, research papers, or in some other textbooks or course, they might call it a simple path. And what we call a walk, they might call it a path. So both terminologies exist, and both are very much in use. And you just need to be very about, you just need to consider which one is in use. So our book uses the second terminologies. That means that path is equivalent to a walk. A simple path is a walk with no repeating vertices or a path, right? And there are some other definitions which are very trivial, so you can just go through them later on. So here's the passage from the book, our course book, that explains this. And what I'll just go and read through this. There is a considerable variation of terminology concerning the concepts defined previously. For instance, in some books, the term walk is used instead of path, where a walk is defined to be an alternating sequence of vertices and edges of a graph. When this terminology is used, closed walk is used for a circuit, uh, and a trail or a path is used to denote a walk that has no repeating edges, replacing the term simple path. So a simple path is the same thing as a trail. When this terminology is used, the terminology path is often used for a trail with no repeated vertex, conflicting with the terminology we have studied previously. So it is the job of the reader to make sure which set of definitions are in used. Okay. So here's another new definition which says a directed graph with no cycles is called a directed acyclic graph, or a DAG for a short. And then we have a weighted graph. A graph with labeled edges is called a weighted graph. The weight represents the cost of an edge. So the weights can be anything from price, distance, time, etc. It's just the cost. It can be the bandwidth of in an internet network graph, in a graph of internet connection, or it can just be anything. It's just the cost or the penalty that you have to pay to traverse that edge. So the lower the penalty, the lower the cost. The highest, the more the penalty, the higher the cost. So it's just the penalty. So a weighted graph is represented by labeling the edges with a number. And this is exactly what we saw when we started this chapter, and we saw an example of the graph. So in the next sessions, we will see what is the shortest path problem and discuss more upon that.